Okay, welcome again. In this lecture, we're going to talk about cache coherence, another fascinating topic in the design of shared memory multiprocessors. And we have a bunch of readings for you. These are some of the readings that are required for understanding Color and Singh book chapter 5.1 through 5.3. Patterson and Hennessy, Computer Organization and Design chapter 5.8 talks about this. It's a relatively short chapter. And two seminal papers. One is Papamarkos and Patel's a low overhead coherence solution for multiprocessors with private cache memories paper, which describes the MESI protocol, which we will discuss in this lecture today, or otherwise known as Illinois protocol, and Loron Lenowski's SGI origin computer, which actually implements some interesting coherence optimizations. This is the SGI machine, SGI origin machine, which was published in ISCA 1997. There are a bunch of recommended readings also, and we will go over these later. One of them is the classical Sensia and Fautrier paper on directory-based cache coherence, which we will cover also. The next one is Goodman's paper on Snoopy cache coherence, using cache memory to reduce processor memory traffic. The next one is Lenowski's paper on Lenowski et al.'s paper on Stanford Dash multiprocessor, which has some interesting coherence protocols. The next one is Milo Martin's paper on token coherence, which we will briefly cover at the very end of this lecture. And finally, the last one is an interesting aspect of coherence, basically how inclusion property in caches actually helps maintaining coherence. It's a paper by Jean-Luc Baer and Wang. Okay, these readings I would very much recommend you to do, and if you're interested in some research topics related to this, I will get back to that toward the end of the lecture. But let's start with cache coherence. Let's start with the basics. Basically, we're talking about the shared memory model, shared memory programming. Many parallel programs communicate through shared memory. Let's say you have a processor that writes to an address, followed by another processor that reads from it. This implies there is some communication between the two. And this is an example. For example, processor 0 is writing to a memory location A, and processor 1 is reading that memory location and printing it later on. So each read, in this case, should receive the last value written by anyone, right? That's what you would expect. This is what the programmer would expect. And this requires synchronization. What does last written mean, right? There needs to be some synchronization. Now, in this case, what if there is an additional caching mechanism? What if memory location A is cached at either end? What does it mean to be last written? Do these updates become visible to processor 1? Well, that's what you would expect, right? The basic question in cache coherence is, if multiple processors cache the same block or same piece of data, how do they ensure they all see a consistent state? In the previous example over here, if memory location A is cached in processor 0's cache, but not in processor 1's cache, or in both caches, when processor 0 writes to memory location A, it updates its own cache. When processor 1 reads it, it should get that update, right? That's what you would expect. So that's the basic question. How do the processors ensure they all see a consistent state? So let's take a look at the problem. We have two processors, processor 1 and processor 2. Processor 2 does a load to register 2 from memory location X. Memory location X contains 1000 in this case. Then processor 1 does a load to memory location X. So it also gets the value 1000. Later, processor 1 does some operation and stores R1 to memory location X, and memory location X becomes 2000 in its cache. Now you have two inconsistent values in the caches, right? Processor 1 has 2000 for the memory location X that's cached in its cache. Processor 2 has 1000 for the memory location X that's cached in its cache. Now if processor 2 does a read, does a load to memory location X, it will access its cache and it will load 1000. But it should not load 1000 because you have an inconsistency in the value. So the caches are actually inconsistent. So somehow we need to ensure that processor 2 actually loads 2000. And then the question is, who should ensure that? This problem is called the cache consistency problem. It's actually different from the memory consistency problem. We had a memory consistency lecture before. Cache consistency ensures that, this is more commonly called cache coherence, basically ensures that the same value, the same memory address that's actually updated by multiple processors are kept consistent across different caches. Whereas memory consistency is very different, right? The ordering of different memory addresses, different memory operations is consistent, is the same, for example, for sequential consistency, is the same for all processors, right? All of the global order, there's a global order of memory operations coming from all processors to all memory locations, and that's the same for all processors. Whereas in cache consistency, we're really concerned with a single memory location instead of all memory locations. So that's the difference. We need to keep the caches coherent for every single memory location, but there's no relationship between different memory locations in the cache coherence problem, right? Whereas in the memory consistency problem, it's a memory ordering problem. Here, the ordering problem is really on a single location instead of many different locations. We'll get back to this, hopefully, but that's the key difference between cache consistency and memory consistency, which we have discussed in a separate lecture. Okay, whose responsibility is to keep this memory location coherent? Is it the software's responsibility or is it the hardware's responsibility? And there have been solutions developed for both, actually, and both may work. So the key question is, can the programmer ensure coherence if caches are invisible to software? This is a very tough one, right? This is actually difficult to do. You could potentially ensure coherence if you actually are doing caching on a virtual memory page basis, and when you're actually accessing a location, you could lock that location, and that would evict some other processor's accesses to that location. That would disable some other processor's accesses to that location. But then, to be able to do locking, those locks need to be kept coherent somehow, right? You cannot cache those locks if you want to ensure coherence at the page level. But basically, the key question is, can the programmer ensure coherence if caches are invisible to software? The answer is no, because if the programmer cannot see the caches, even cannot manipulate the caches, it's very difficult, well, I would say impossible, to ensure coherence. What if the ISA actually provided a cache flush instruction? And we'll talk about a couple of them. I'll not go into the detail, but this is mainly for to enable you to think if the software can handle this problem with some instructions. One instruction could be flush local A. And the idea is, basically this flushes or invalidates the cache block containing address A from a processor's local cache. Let's take a look at this example very quickly. You have this processor 1, you have this processor 2, and let's say they both cache block A, and you want to keep them coherent, right? What if you have a flush local instruction? Can you keep them coherent? If this processor writes to address A, makes it 2000, you want to ensure that this processor gets the 2000 value or doesn't read the 1000 value, right? Because that's the latest value that's written, as we've shown earlier. If you have a flush local instruction, somehow you can use it. This processor 1 somehow needs to predict when to use that instruction, right? If someone actually writes to that location, this processor 1 needs to execute that flush local instruction such that it gets rid of this memory location in its cache. And that's impossible to do almost, right? How do you actually figure out that somebody else is writing to some other location when you're executing some totally different thread? So this is difficult to do. The second is flush global instruction. Basically, this flushes or invalidates the cache block containing address A from all other processors' caches. Let's take a look at that. This sounds more promising, right? Why does it sound more promising? Because this can be executed by the processor that is actually writing to that location. So, for example, let's say you have this this block cached by both of the processors. Let's say processor 2 is going to write to A, but before writing to A, it issues a flush global instruction, flush global A. And the job of that instruction, the hardware implements that instruction such that it goes through every cache and invalidates the block. So this is gone. The val bit is set to 0. Now this processor can do a store to A, 2000, right? Store 2000 into A. Now this can be updated to 2000, right? Beautiful, right? Well, not so quiet, because there is some window of vulnerability between these two instructions, right? What might happen is, after this flush global is executed, and this block gets invalidated, right after that, this processor 1 can actually do a load, right? And it can actually load A into R1. And it can get the value 1000 from memory, let's say, right? Because it's actually missed in the cache, and you have no awareness of it's present in the other cache. So the memory still has 1000, remember? So it gets the value 1000 after flush global, after this gets invalidated. But before the store, this processor does a load and reloads back A's old value from memory, 1000. Now this processor does a store to A with the value 2000. So now you have inconsistency again, right? So flush global doesn't work because you have this vulnerability, right? And that vulnerability can be really bad. What if this processor takes an interrupt at the end of flush global? So you really need to make things atomic to be able to do that. And actually, I'll let you think about how to make this work. But the solution you get to will be closer to cache coherence, which we will discuss. Basically, with this mechanism, flush global actually is providing an invalidation mechanism for blocks that are cached, right? And we will see that this hardware support that's needed for invalidating other caches will be used in some of our coherence protocols. But this is difficult to do in software. With every store instruction, it's very difficult to do a flush global because you need to guarantee correctness, and that correctness is difficult to guarantee. Well, you can imagine methods of guaranteeing that coherence, but that's not the subject of this lecture. If you actually can make atomic updates, meaning atomic flush global and atomic store, perhaps you can make this work, right? But then the hardware needs to guarantee some atomicity in both flushing and then storing at the same time. And that requires significantly costly hardware. So I'd encourage you to think about this if you can actually do this in software, but that's going to be quite difficult to do that. Let's take a look at one last instruction, which is this flush cache instruction that I show over here. Basically flush or invalidate all blocks in cache X. It has a very similar problem that plagues flush global. Basically, what if you invalidate all of the caches? Well, then there's a problem, right? It's inefficient. If you actually invalidate the entire cache, it's inefficient because when that processor loses all the locality benefits of caching if it actually has locality, right? So flush cache X is a heavyweight solution, but it actually doesn't work also because it has similar issues. Even if you flush someone else's cache, that someone else can load that value again from memory, right? So basically, in coherence, you need to ensure that someone else doesn't load the stale value. And to be able to do that, you need some atomicity over here. And hardware, if you actually provide this coherence mechanism in hardware, then you can actually achieve that atomicity a little bit more easily. So it's very difficult. So the key conclusion is it's very difficult for the software to keep these values coherent in the caches, even if it has some of the support for these instructions. Hardware simplifies software's job. And one idea, which we will talk about, is basically invalidate whenever this processor actually writes to a cache block, the hardware implicitly sends invalidation signals to all of the other caches saying that other caches invalidate this block that this processor is writing. And that's the idea. Once that happens, this processor can directly write to that block, right? Then the key question is, how do you support this in an atomic way, right? And that's our idea. That's the idea behind cache coherence. Right? So this is again, if you look at the slide, this is again a big trade-off between the programmer and the microarchitect. And we will see that again. We have seen this in memory consistency, right? And actually, I will say architect, not necessarily microarchitect. Basically, programmer's job is really hard if you have caches and those caches need to be kept coherent, and hardware doesn't provide any support. Whereas hardware designer's job is really easy in that case, right? Because the hardware designer doesn't need to provide any support for keeping the caches coherent. Whereas if the hardware provides support, then the microarchitect needs to design this protocol such that it operates correctly to keep the cache's values consistent with each other for a given memory location. Whereas the programmer's job is much easier. They don't need to worry about this hardware caching and keeping those caches coherent. Okay? So this is another trade-off. So let's take a look at our very simple coherence scheme. Basically, we were talking about invalidating when a processor actually writes to a block. And that's the idea. Caches snoop each other's write and read operations. If a processor writes to a block, all others invalidate from their caches. Very simple, right? Beautiful. And a simple protocol looks like this. Each block has two states. valid or invalid. And let's assume that this actually a state diagram. The state diagram shows the transitions between these two states, and the cache is write through and write no allocate. Basically, write through means that any write that just happens to the cache also goes to memory, and also no write allocate. Basically, when a cache block is not present, if you're doing a write, if you're doing a store from the processor, that block is not brought into the cache. The block is written directly in memory. Right? And there are many design choices related to this, which we've covered in 18447. And you can look at the lectures from spring 2013 again on caching and advanced caching to actually be able to think about both write-through caches and no-write allocate caches. I'm not going to cover that over here. But this is how a block transitions its states in the simple protocol. And there are several actions. Processor can read the block, the processor can write the block, and these are signals that are sent on the bus, basically to enable other processors to see what this processor is doing. Basically, for example, if the block is invalid, let's say, and this processor reads that block, what happens is, this is the signal. The processor sends a processor read signal, which translates into a bus read signal on the bus. All processors see this, and the block becomes valid. Now, if this processor wants to write to this block, let's assume that another processor also reads the block. If the other processor reads the block, basically it also sends a processor read signal, which sends a bus read signal on the bus, and the block becomes valid. Now you have two processors that have the block valid, right? Now let's say one processor writes to the block. It basically sends a processor write signal to the cache, and the block stays valid, and this generates a bus write signal at the same time out of the cache on the bus. Now other processors see this bus write signal, and another processor which has the block valid in its cache sees this bus write signal and transitions into the invalid state. That's basically invalidating the block that is being written by some other processor. Right? That's the idea, basically. If another processor has the block in invalid state, then you don't really care, right? Basically, even if it receives any signal, it basically stays in the invalid state. Right? That's the idea. Okay? Basically, this requires, of course, every cache block to be tagged with these bits and the state machine to actually take into account these signals. And we will see more sophisticated coherence schemes. So this is a very simple coherence scheme. This is one solution to cache coherence, but let's also cover some solutions to cache coherence that I believe are non-solutions. One solution is basically, why do we care, right? No hardware-based coherence. Let's not provide hardware-based cache coherence. And leave it to the software to keep the caches coherent. Well, this is not a solution to cache coherence. This is another solution to cache coherence, but this is really punting the problem to the programmer. And as I said, it's very difficult for the programmer to actually keep the caches coherent. Assuming coherence is an important thing that's needed by applications. If you have shared memory applications where the data is exchanged between processors quite often, or even once in a while, and that exchange is important, then coherence is likely important. And assuming this is the case, not providing hardware-based coherence is actually a bad solution or a non-solution because you're not providing cache coherence. If there is no data exchange between the processors, then and your data is partitioned nicely and each processor is operating on its own data in its own cache, maybe it's okay to provide no hardware-based cache coherence, right? If that's the design point of your processor. But many general-purpose processors are not designed for that design point. In many general-purpose processors, you actually have shared memory and different processors execute threads that are cooperating with each other and operating on shared data. So it's very difficult to punt the problem on software. But the upside is it makes microarchitect's life easier because the microarchitect doesn't need to provide for this protocol an example of which we've discussed in the previous slide. It makes the average programmer's life much harder. Now, does the programmer really need to worry about hardware caches to maintain program correctness? That becomes difficult. And this leads to overheads in ensuring coherence in software. There are ways of doing this. For example, you could do it through page locking. You could do it through lots of invalidations and some support in hardware to do those invalidations. but it's expensive to do this. And in fact, processors that have provided no cache coherence in hardware have been very difficult to design and very difficult to program. One example of this is the IBM Cell processor. IBM Cell processor is a 9-core machine. Actually, it's an asymmetric machine. It basically has a control processor, and it has 8 synergistic processing elements. And this is the control processor. I think this was called the primary processing element. And these synergistic processing elements actually had caches. They're actually scratchpad memories that the programmer needs to keep coherent. And that coherence needs to be also kept by a programmer across all the caches between the primary processing element and synergistic processing elements. Basically, these are scratchpad memories, and the programmer needs to ensure that coherence is not a problem, which means that there is no solution to coherence. And this machine has been very difficult to program. One of the reasons has been the lack of a hardware-based coherence scheme. So, okay, it's very difficult, and there's also a lot of overhead in ensuring coherence in software. Let's say you can do that, right? You can say, I actually bring a page over here, and I lock that page such that only this processor can access it. And there is overhead. If another processor wants to access it, now you need to do synchronization at that high level, and that's tough to do. Well, that has a lot of overhead to do. The second non-solution to cache coherence is, well, why have private caches, right? Why not have this, basically? Instead of having 2 caches, have a shared cache. Well, now you don't have a problem because the cache block that you're caching is not replicated across different caches, right? There's only one location, one cache location where the block can be accessed. Right? And you can imagine that you keep adding processors into the system, and you have 1,000 processors that share a single cache. Well, why not? Why not scale the system more? Add more processors, add 1,000 processors, have a total of 10,000 processors, and they all share a single cache. You see the problem, right? Basically, the upside is no need for coherence because the block doesn't get replicated across different caches because there is only single cache. The problem is the shared cache becomes a latency and bandwidth bottleneck. How do you design this cache that's huge and also shared by 1,000 processors? Right? So it's very hard to design a scalable system with low latency cache access this way and high bandwidth cache access this way. You can actually bank the cache to get access, but again, that sharing, even that banking overhead makes the system very high latency and difficult to design also. So we would like caches that are not shared for this reason, or we would like caches that are not shared for this reason so that we can scale the system nicely, right? Then we will need to provide a solution for cache coherence. So this is a non-solution. Okay, so how do we maintain coherence? Basically, we need to guarantee that all processors see a consistent value, in other words, consistent updates for the same memory location. Again, the key is same memory location. Which means that writes to location A by a processor 0 should be seen by processor 1 eventually, and all writes to A should appear in some order. There are 2 key requirements for coherence, cache coherence. One is write propagation, and the second is write serialization. Write propagation means there should be a guarantee that updates to a memory location will propagate to all processors. And write serialization, all caches at least that have that location. Write serialization means there has to be a consistent global order for that location by all processors. And again, this is for that particular location. All the writes should be serialized, and all processors should see that the same order of writes for that particular location. Okay, which means that you need a global point of serialization for the store ordering. And you need this global point for actually just that particular memory location. You don't need it for all memory locations. In memory consistency, remember, for all memory locations, you need some ordering that's consistent across different processors. We're not talking about for all memory locations. We're talking about a single memory location and keeping that value consistent for that memory location in different caches. So you need a single point of serialization for that memory location's store ordering. So the basic idea of hardware cache coherence is when a processor writes or updates a memory location, it basically broadcasts this update or write to all processors. And when I talk about processors, I'll talk about caches because caches have to be there. I'm going to associate a processor with its private cache. Right. Another cache that has that location sees this update or write signal saying that, oh, some other processor is actually writing to this location, and either updates its copy if the data is broadcast or invalidates its copy. So that's the basic idea. So there's a trade-off that just appeared from what I discussed, right? The cache can either update its copy with the data value that's written or invalidates its copy. Well, this actually brings us into the first trade-off in coherence protocols: update or invalidate. The key question is, how can we safely update replicated data? There are two options for this, and the data is replicated. When I talk about replicated data, basically you have a memory location A replicated potentially in all processors' private caches, right? And you would like to keep that memory location consistent, the value the same. There are two options. One is an update protocol. You push an update to all copies. When this processor writes to A, there's some data, right? The data value is, let's say, 10. It not only writes 10 over here, but it also broadcasts or tells everyone somehow. Broadcast is not necessary, as we will see. Tells everyone that, oh, I'm writing to A the value 10. If you have that in your cache, please capture it. And that broadcast, basically every cache checks independently its own locations and tag stores, and if A is present, in which case it is, they basically capture the value. Initially the value may be 0, and they capture the value and the value becomes 10. Right? This is an update-based protocol. Basically, you push an update to all copies. On the other hand, an invalidate-based protocol is, again, requires a broadcast, but doesn't require the broadcast of the data. Basically, initially we have memory location A in all of these caches. And let's say initial value 0, and this processor writes to A the value 10. It basically says, I'm going to write the value 10 to this location. It sends a bus write to memory location A. It doesn't broadcast the data. The whole point of this bus write is to tell the caches, if you actually have location A in your cache, invalidate it, because I'm going to write to that block. And these caches, when they snoop the bus, this is the idea of snooping, we will see that this is one protocol, they actually invalidate the block. Basically, the tag store sets the valid bit of that block A to 0 in this case. So this is the invalidate-based protocol. Ensure there is only one copy by invalidating every other copy, and then update it. Okay? And then this processor can now update it. So basically, I've already described this, but on a read, if local copy isn't valid, you put out a request. This is the general read, what happens in a coherence protocol, right? If you have a cache miss, you put out a request, basically. If another node has a copy, it returns it, otherwise memory does, right? On a write, let's say, the processor reads the block into the cache as before, and if you have an update protocol, what happens is, the processor writes to the block and simultaneously broadcasts the written data to the share, such that every share that also has the copy in its cache gets the updated value. So this is called share, not some terminology. Basically, you have shares. Share means that this is the caches that also contain the same block that is either read or written to. In this case, written to, right? So in this case, all of these caches are shares. Well, assuming that A is actually present over there, right? Okay. Basically, other nodes update their caches if data was present, if that block was present. On the other hand, if there's an invalidate protocol, as I showed you earlier, the processor that's writing to the block writes to the block and simultaneously broadcasts an invalidation request to of the address to all of the shares. And all of the shares, when they see the invalidation request, clear the block, invalidate the block from their cache. So basically, which one do we want? Do we want an update-based protocol, or do we want an invalidate-based protocol? And the answer is it depends. Basically, how does the program work? What is the write frequency and the sharing behavior of these different blocks? And perhaps you want sometimes an update-based protocol, sometimes an invalidate-based protocol, depending on the usage of the block. So when do you want an update protocol? Basically, if the share set is constant, let's say, maybe I'll erase this over here so that we can clear the board. If the share set is constant and the updates are infrequent, maybe you do want this update-based protocol, right? Because in that case, what might happen is only a few processors actually share the block, and updates don't happen very frequently, and they keep reading the block after that, which means that all processors need the block even after it's written, right? Let's say you have processor 1, processor 2, processor 3, processor 4, processor 5, and these two processors happen to like A, block A, and they keep sharing it, and they keep reading from it. It's very read intensive. It's very read heavy. This processor does a write once in a while and updates it to 20, and after that they still keep reading it. In that case, it's good to have an update-based protocol that says, oh, please update your copy when I write to it, right? In that case, after that, the processor still continue to keep reading it. Basically, in this case, the blocks are, they're mostly reads to the blocks. The share set remains constant, and that way you can actually push your updates to another share, and they can get the new copy without getting a cache miss later on. Right? If you actually invalidated in this case, this processor needed to get a cache miss to read the block. Right? So it'll take longer for this processor to get the block that's going to be needed again anyway. The problem with an update protocol is if you actually push an update to some other processor, but if the data is actually again rewritten by this processor, then you keep pushing the same updates for the same block over and over. And this basically wastes bandwidth, right? Basically, it leads to useless transmission of data. It wastes energy also. So basically, if this processor keeps writing to a block over and over and over and over, then it doesn't make sense to keep sending updates of that location because there are no intervening reads coming from other processors. Right? So this is a case where update protocol doesn't work too well, right? Because it's wasting a lot of bandwidth and energy. And update protocol also leads to a write-through cache policy. Right? If you think about it, you're actually writing through the cache to some other cache, which means that this bus becomes a bottleneck. Right? You keep exercising the data bandwidth of your updates of your bus, assuming you have a bus in this case. Okay. Okay. Invalidate protocol, on the other hand, is when a processor sends an invalidation request. After that, it has exclusive rights to the block. It can do whatever it wants with it, right? So it can keep writing from the block, writing to the block exclusively without disturbing any other processor. And this is powerful because in the end, only cores that keep reading the block, each write, reading after each write retain a copy, right? For example, if you have an update-based protocol, if a block, let's say all of the blocks, all of the caches actually have the block initially, and this processor pushes an update to all of those caches. Now you have the location updated. Let's say this processor pushes another update. Now you have the location updated, right? And if only two processors are reading the block, then you've actually done updates to all of these caches unnecessarily, right? That's kind of a waste, right? It basically not only wastes cache space, but it also wastes energy, right? Whereas with invalidation, only the cores that actually keep reading after each write retain a copy. So this is more efficient, it could be. The problem with invalidation-based protocols is if write contention is high, if there are lots of writes that are happening, then this leads to ping-ponging, right? Basically, it leads to rapid mutual invalidation and requires, right? So this processor can write to this block, it invalidates everyone, and later this processor writes to the same block, it invalidates everyone, and there's lots of ping-ponging of the data that's moved. With an update-based protocol, let's assume that two processors are doing that ping-ponging. Let me show you an example where invalidate-based protocol is actually worse than an update-based protocol. Let me clean up my mess over here first. But basically, let's say you have these two processors. They are both happy sharing this A. And what happens is, let's say this processor is writing to A. It invalidates A over here. And later this processor needs A, and it needs to do a write to A. It needs to write 300, let's say. In that case, it first invalidates this and writes 300. Right. And later, this processor happens to want to write 400 to A. It basically invalidates this and writes 400. And later, this processor wants to write 500. It invalidates this and writes 500. Basically, this is what happens in an invalidation-based protocol. You need to send an invalidate to another cache to write, and you need to bring the data and write to the block. Right? Basically, it takes an invalidate, fetch, and write. This is an invalidation traffic. This fetch and invalidation are kind of extra. Whereas if you had an update-based protocol, what would happen is, initially you start out with 100, let's say. This processor writes 200. It not only writes 200, but it also sends 200 here, right? Basically, you push the data. On the other hand, when this processor now wants to write 300 to the block, it has the block in its cache. It's a cache hit, right? It doesn't need to fetch the data again, because the data was pushed through the protocol into its cache. Now it writes 300 and pushes the data through the update-based protocol to the other cache that has it. Basically, update-based protocol, in this case, gets rid of this extra fetch. It doesn't have the invalidate. It basically has the push of data, update of data in their core, and then write. Actually, it's write first and then push the data, right? That's how it works. So this is a case where an update-based protocol is better than an invalidate-based protocol. If write contention is high, if you have this kind of ping-ponging, if you have an invalidate-based protocol, you have ping-ponging. If you don't have an invalidate, if you have an update-based protocol, there is no ping-ponging, right? You don't need to invalidate, fetch, invalidate, fetch, invalidate, fetch. That doesn't happen. So these are actually two coherence protocols, and many coherence protocols make a trade-off between that. You can imagine adapting this to the blocks, and you can imagine different policies, and I'll encourage you to think about them. Maybe you'll come up with some new mechanisms. For example, if a processor doesn't need a block after some point, maybe it should invalidate it in its own cache, right? Or if a processor predicts that someone else will need the block, maybe it sends a request to actually update that block's cache. Okay? You can imagine different kind of mechanisms that basically break the trade-off between update and invalidate. But that's more researchy, and I'll encourage you to think about that if you'd like to do a research project. So let's cover two cache coherence methods that are very basic. The key question is, how do we ensure that the proper caches are updated? And there are two big cache coherence methods. One is Snoopy bus. This is the idea that I've kind of discussed over here. This was proposed by Goodman in the ISCA 1983 paper that I described. That's the MSI protocol. And it was improved by Papamarkos and Patel, Janak Patel's seminal paper in ISCA 1984 with the MESI protocol. Basically, Snoopy bus, you have a bus-based machine. You have a single point of serialization for all requests. And if you have this, it's very easy for all of the processors to observe all of the other processors' actions, right? For example, a processor 1 can make a read exclusive request for A on the bus, and processor 0 sees this and invalidates its own copy. Every processor can see that invalidation request, read exclusive request. Read exclusive in this case means I'm going to read this data in an exclusive way because I want to write to it. I want this cache block to be mine only. I wanted it to be exclusive, and we'll get to that. On the other hand, directory-based protocol is fundamentally different. This is originally proposed by Saint-Cyr and Fatrier in Transactions on Computers in 1978. The idea is you have a single point of serialization per block that's distributed among nodes. That's in memory, let's say. Here, with a bus-based protocol, you have a single point of serialization for everything, whereas for a directory, you have another location that's separate, that contains information. I'll draw a separate thing over here. A directory that's close to memory, and you can have multiple pieces of memory that's distributed, right? I'll show you one piece. This directory keeps information about every block that is part of this memory. And it keeps information about who is sharing this block and who is owning this block, who has a copy of this block in its own caches, right? Basically, it's a separate point of serialization for every single block, and this point of serialization could be different. For example, you can have memory space partitioned, and you can have another memory over here. Memory location 0 through n-1 can be here, and memory location n to n-1 can be here. And you have directory over here that has information about the blocks that are addressed between n to n-1, right? And if a processor actually needs a location, let's say 0, it basically sends a request to the directory saying, directory, could you please tell me where I should get this particular location 0 from? This is the point of serialization of request for that memory location, right? This is distributed among the nodes. Processors make explicit requests for the blocks. Processor says, I want this memory location 0, and directory, can you tell me which caches have it? Or if I want to write to this memory location 0, directory, can you actually invalidate all of the other caches? That's the idea. And the idea is that this directory keeps track of ownership of the cache blocks, basically a share set of the cache blocks, and directory coordinates the invalidation appropriately, or the updates. So update versus invalidate is actually orthogonal to directory versus update versus invalidate is a design choice that's orthogonal to Snoopy-based protocols versus directory-based protocols. Because the directory can say it invalidates, or directory can send updates to all of the shares. Okay? Basically, one example is for processor 1, for example, in this case, asks the directory for a block, for an exclusive copy, saying that I'm going to write to this block, and directory asks processor 0, for example, to invalidate that copy because processor 1 is going to write to it, right? And waits for the acknowledgement of processor 0 saying that, oh, I invalidated my copy, and then responds to processor 1 saying, oh, you have the only copy, now you can write to it, right? So directory basically coordinates all of the actions that are happening on a particular cache block. So this is kind of nice, right? It's a single point of serialization for a given cache block instead of single point of serialization for everything. So as a result, this is more scalable, right? The directory is more scalable because the single point of serialization for different cache blocks can be in different places. They can be distributed across the system. They don't have to be done across a single bus. Whereas Snoopy bus is less scalable because it requires this Snoopy bus. Basically, when a cache writes to, when a cache does something to a cache block, that something needs to be visible, broadcast to all of the other caches in the system. Okay, now let's take a look at these in a little bit more detail. Let's cover directory-based cache coherence. I've given you the basic ideas, but I'd like to go over a little bit more detail. Basically, the idea is a logically central directory keeps track of where the copies of each cache block actually reside. And caches consult this directory to ensure coherence. An example mechanism, basically, for each cache block in memory, let me actually draw this in a little bit. You store the share set, and share set plus 1 bit. Let's say you have P processors in the system. You basically have P plus 1 bits for each cache block in memory. And basically, these are presence bits. So let's say 1, 2, 3, 4, 5. Let's say we have 4 processor system. You have 4 plus 1 bits. And basically, each bit over here designates whether different processors' private caches actually have this block. Initially, if the block is not cached, these are all 0. And this bit designates whether any processor has the block as exclusive. Right? Okay, exclusive bit, the purpose of this is, this indicates that the cache, a cache has the only copy of the block and can update it without notifying others. That's the purpose of the exclusive bit. And this makes life easier because this enables that cache to update that block without consulting the directory, right? The directory knows that this cache has an exclusive, so it can do anything to that block, and the directory knows that that cache, it should consult that cache. If anyone else requests that block, that cache has the up-to-date copy, right? Because that cache can do anything to that block without notifying others. So on a read, what happens is the directory gets a read request from a processor and checks these bits, assuming that there's nothing here. On a read, the processor basically sends the block, the directory sends the block to the processor and sets the bit saying that this processor now has a copy of this block, right? On a write, what the directory does is it invalidates. It basically checks these bits, figures out all of the processors that actually have the block, and sends invalidation requests to all of the caches that have the block and resets their bits and waits for acknowledgement. It needs to wait for acknowledgement because it's going to be a very scalable system, right? It's not a bus anymore. It may take a while for the directory's invalidation request to go all the way to all of these processors that have their bits set. Let's say these 3 processors have their bits set, and there's a write request coming in from, let's say, it doesn't matter which processor, let's say from processor 1. In this case, the directory sends an invalidation request to processor 1 and processor 2, right? Processor 1 and processor 2. And it may take a while for that write request to go over, to invalidate request to go all the way to those processors. So the directory requires the acknowledgements to come back. After all the acknowledgements come back, then this directory can give exclusive access to processor 0, saying processor 0, now you have exclusive access, now you can write to the block. Right? That's the idea. You can see that this is more scalable than a bus, but there's indirection that's happening through the directory. And basically, you have an exclusive bit associated with each block in each cache also that enables the block to write to, that enables the cache to write to that block without notifying this directory. Okay? So every cache, if you look at the processors, and I have again 4 of them over here, basically every cache block has an exclusive bit saying, is the cache block exclusive? Right? And the purpose of this bit is, if the bit is set, the processor doesn't need to consult the directory. It checks the bit, oh, I have the block in exclusive state, which means that the directory ensured that I'm the only processor that has the block, and I can do whatever I want with it, and the directory is not going to, is going to ensure correctness. For example, if someone actually requests this block, the directory is going to ask this processor and get the block and reset the exclusive bit. Right? That's how exclusive works. The purpose of exclusive is to enable the processor to update the block without notifying others, such that you avoid this indirection through the directory. Okay, let's take an example over here. This is the example that I show on the screen over here. Basically, we have 4 processors and 1 exclusive bit. This is the directory, and you have this for every block in memory, basically in the directory. In this case, for this particular cache block, block A, all of the bits are set to 0, which means that no cache has the block. Let's say processor 1 takes a read miss to block A. In this case, processor 1 sends a request to the directory that contains block A, and the directory sets the bits associated with processor 1, in this case this bit, and sends the block to processor 1 from memory. Okay? Now processor 1 has the block. After a while, processor 3 takes a read miss. Processor 3 notifies the directory saying that I would like to read from block A. Directory receives the request. It basically sets the bit for processor 3 saying that processor 3 also has the block. Now the directory's responsibility is also supply the data somehow. And the directory can choose to supply the data from memory in this case, because the block is in memory. The version of the block that's in memory is consistent with the the version of the block that is in processor 1's cache, right? The directory can decide to take the block from memory and send it to processor 3's cache, or the directory knows that processor 1 actually also has the block, and the directory can take some action, right? The directory can say, processor 1, processor 3 is requesting this block. Why don't you send your block A to processor 3? That's the idea, right? Why would the directory ever do that? Well, let's take a look. You have the directory here, let's say, and you have main memory. And what might happen is you have processor 1 and processor 3, let's say they're very close to each other. The directory, it may take a long while to access block A from memory because actually maybe there's a huge number of requests queued up. Or maybe memory is just slow to access, right? In this case, processor 3 is requesting A, and the directory knows that processor 1 actually has a copy of A, and processor 3 doesn't have a copy of A yet. And the directory knows that processor 1's copy of A is consistent with what's in memory. And the directory can tell processor 1, send your copy of A to processor 3. And processor 1 can actually send that copy to processor 3. And this is called a cache-to-cache transfer. So you can optimize this directory protocol because directory has a lot of knowledge. It can actually be augmented with knowledge of how fast can the cache-to-cache transfer happen between these two different processors, between any processor in the system, right? So that's the idea. So this gives you a lot of flexibility because the directory has a lot of knowledge about the blocks. Now it can do these optimizations, and we will see that again. So let's take a look. Now processor 1 and processor 3 have copies, and processor 3 somehow got the copy of block A. And in directory, I guess I'll now have the directory over here. Processor 1 and processor 3 have the copy, and none of them have an exclusive, which also means that the copies that the processors have are consistent with the data that's in memory for that block, right? Because no one has an exclusive state. No one is writing to it. Okay, now let's see an interesting case. Let's say processor 2 takes a write miss, right? Now we're in this state, and processor 2 sends a request saying, I want to write to A, which is also a read exclusive request, actually. The directory's first job is, oh, somebody's writing to A, and some other caches actually have these blocks. Let me first invalidate them. Actually, you could do update also, but let's look at an invalidate-based protocol. Directory sees that processor 1 and processor 3 has these block that processor 2 wants to, and basically sends an invalidate request to all of the processors whose bits are set for this particular block. And these processors, when they receive the invalidate request, they invalidate A from their caches, they purge it, they get rid of it, and A cannot be modified because this is a read shared block, because it's not exclusive in any cache. And they send acknowledgements to the directory saying that, oh, directory, we acknowledge the invalidation. We've gotten rid of A from our caches. And these invalidations arrive. Then the directory sets these bits for processor 1 and processor 3 for block A to 0. Now, the directory can give ownership, supply that write request. Basically, the directory can tell processor 2, you have the block, I'm going to send you the block, and you're going to have it as exclusive, so you can do whatever you want with it because you want to write to it. That's the idea, right? Basically, if you look at this, processor 2 now has the exclusive copy of the block. It sets the exclusive bit. The directory sets the exclusive bit. And in processor 2's cache, well, I should add processor 2 over here. Now you have block A because it was sent by the directory, and its exclusive bit is also set. Now processor 2 can write to the block over and over without notifying the directory. Okay? Okay. Now let's say processor 3 takes a write miss. What happens in this case? Now the directory can do another optimization, right? This processor 3's write to A comes to the directory, and directory checks its bits. Oh, processor 2 actually has the exclusive copy, right? And that has the only copy and processor 3 wants to write to it. What do I do? Right. Well, there are multiple options here. What the directory can do is, directory can first say, processor 2, you have the up-to-date copy, send it to me. And the directory in that case gets the up-to-date copy. Processor 2 doesn't have it anymore. And later the processor, and this is also 0, because now the directory has the up-to-date copy and no one has it. And after that, the directory can say, processor 3, I'm going to send you this copy that I just received from processor 2, and you'll have it as exclusive. Right? And processor 3 will have the block as exclusive. That's one way. And that's the final state. Basically, processor 3's bit is set. Or what might happen is processor 2, remember this was the initial state, processor 2 had the block as exclusive. The directory, when it receives the write request, can tell processor 2, processor 2, processor 3 is actually requesting this block. So why don't you do this? Why don't you actually send the block to processor 3, and I'm going to give exclusive rights to it, and also invalidate the block. So that's certainly possible also with a directory-based protocol, right? That way, processor 2 it doesn't have the block anymore, after acknowledgements are done, of course. Processor 3 will get the block through a cache-to-cache transfer, and memory will never get the block, and actually it doesn't really need to get the block, right? Because processor 3 is requesting it to write to the block, right? Okay? So this is one protocol. You could, of course, extend this such that you can have multiple shares that have some access, but we're not going to get into that. This is a very simple directory-based protocol. You can make it more complicated such that both processor 2 and processor 3 maybe have copies, right? Of course, that works if you don't have write sharing, if processor 3 doesn't want to write. But okay, you can think about that. And later, let's say processor 2 takes a read miss. Well, remember processor 2 was invalidated. If the processor 2 takes a read miss, then what the directory does is it can tell processor 3 to send the data to processor 2, right? Processor 3 basically can supply the data to processor 2. And there may be other options also. And processor directory actually, well, at that point you have shared data. So the processor 3 also supplies the data to directory. Right? Now you have processor 2 and processor 3 having the data. And directory also updated because for the semantics of this protocol, 0 means that directory has the up-to-date copy. Right? You can actually change the semantics by adding more bits. And we're not going to talk about that. But you got the basic idea, hopefully. Okay? So let's take a look at the opposite coherence scheme, which is Snoopy cache coherence. And the idea we've already talked about is all caches snoop all other caches' read and write requests and keep the cache block coherent. Which means that each cache block has coherence metadata associated with it in the tag store of each cache. This is easy to implement if all caches share a common bus. Remember, with the directory, we didn't care about the interconnect. These messages could arrive on any interconnect. It doesn't matter. There needs to be no ordering. Right? Whereas, in this case, we need the snooping. All caches snoop all other cache read-write requests. And this is easy to implement if all caches share a common bus. If there is no shared common bus, you need a virtual bus, which means a totally ordered interconnect. And that becomes difficult to design if you don't have a bus. Okay? Each cache broadcasts its read and write operations on the bus, as we've discussed earlier. And this is good for small-scale multiprocessors because if you have a bus, it's hard to scale that to 1,000 nodes. Why? If you have 1,000 nodes and they're communicating with a single bus, now you have lots of electrical loading on the bus, right? So the bus runs at a small frequency. And there's a lot of contention on the bus too. When actually these two processors are communicating, you cannot transfer anything else on the bus because the bus is shared across all processors. So bandwidth contention becomes very severe. So it's hard to scale a bus to a large-scale system, though this is good for small-scale multiprocessors. Well, if you would like to have a 1,000-node multiprocessor, then you need a more scalable interconnect. And implementing Snoopy-based cache coherence on a more scalable interconnect is not impossible, but it's difficult because now you don't have this bus where things are broadcast. Basically, this is a broadcast-based protocol. You need to broadcast the invalidates or broadcast the updates to all other processors in the system. And that becomes difficult to do it in a very ordered fashion, because the order needs to be preserved also. If you don't have an ordered interconnect, a totally ordered interconnect like a bus. So this is the example. Basically, I've already shown you this, but you have processors and caches, and you have coherent state bits in the tag store, and you have a shared bus. Each cache observes its own processor and the bus, and changes the state of the cache block based on the observed actions by the processor as well as the bus. Right. There are processor actions to a block. Processor can read the block. That's the processor action over here. And processor can write to the block. That's the processor action again that's coming from here. And there are bus actions to a block coming from another processor. And this is where these are the actions that the processor snoop. There could be a bus read, indicating that some other processor is reading this cache block. There could be a bus write, indicating that some other processor is writing to this cache block. This is also called bus read exclusive. So read exclusive and write, you can treat them the same. Okay, we've seen this simple Snoop-based cache coherence protocol. I'm not going to cover this. This is the valid-invalid cache protocol. Right? Basically, whenever a processor writes to a block, all other processors invalidate the block from their caches. A more sophisticated protocol is the MSI protocol. Basically, you extend a single valid bit per block to 3 states. Modified, cache line is the only copy in the system, and it's dirty, right? Basically, no other cache has this block in their caches. And memory doesn't have the up-to-date copy, doesn't necessarily have the up-to-date copy. That's the semantics of this state. Shared, cache line is one of several copies. And invalid, the cache block is not present, right? Shared state means you have the cache line can be present in one or more caches, right? It can be one, it can be also more. We don't know, right? And we'll take a look at that. Basically, when there's a read miss, the processor makes a read request on the bus and transitions the block to the shared state. When there's a write miss, the processor makes a read exclusive request on the bus and transitions to modified state. And when a processor snoops a read exclusive request from another writer on the bus, it must validate its own copy if it has a copy. So this is exactly the same as what I described earlier, right? Except I'm not talking about read request, read exclusive request, right? Now, if you're in a shared state, you can go to the modified upgrade without rereading the data from memory by invalidating, right? Because the processor actually has the data as shared. It already has the data in its cache. It doesn't need to reread it. It can just invalidate all of the other processor's caches that contain that particular block, right? Okay? This is the state machine for the MSI protocol, right? And I'm not going to go over this, but it's very simple, basically. But I'd like to show your attention, draw your attention to one thing. If a block is invalid, and if a processor reads that block, basically what happens is it sends a processor read, obviously. The block goes to the shared state, and the processor sends a bus read signal out. Okay? When any other processor sees a bus read signal, what happens in the modified state over here is the processor sees the bus read signal and it flushes its data from the cache, meaning that supplies that data to that cache, and it also moves to the shared state. Now, if no other processor has the modified state, if this processor will have the only copy, and it will move to the shared state, right? So the semantics of the shared state is one processor or more can have this block in its cache, and that's exactly the problem with the MSI protocol, right? The processor doesn't know whether it has an exclusive copy of the block. Right? So you can go through the state diagram. I'm not going to go through this in detail, but I'd encourage you to study the state diagram really well to understand the coherence protocol. We've studied this in 447, but here it's even more important to understand the coherence protocols because we might look at some optimizations later on. So the problem is that with MSI is if a block is in no cache to begin with. Let me draw the 4 processors that I like. Processor 0, 1, 2, 3. Let's assume that a block is in no cache to begin with, right? On a read, the block immediately goes to the shared state. Let's say we read block A, it immediately goes to the shared state, right? Although it may be the only copy to be cached. In other words, no other processor is ever going to read this block, for example. Think about that case. Why is this a problem? Well, suppose the cache that read the block wants to write to it at some point, and no other processor has the block. What does it need to do? It needs to broadcast and invalidate regardless of whether or not it has the block, it has the only copy of the block cached. Right? Make sense? Basically, it needs to broadcast this invalidate signal even though this cache has the only copy in the system other than main memory. Why? Because the shared state doesn't tell this processor enough information. The shared state says, oh, any other processor can also potentially have the block in its cache. That's why this processor needs to ensure that when it's writing to this block, it needs to invalidate. So that's the problem. Basically, if the cache knew it had the only cached copy in the system, it didn't need to send this invalidate. It basically would have updated the memory location silently without notifying anyone else, right? The problem is when you send this invalidate, you're occupying a lot of bus bandwidth, right? It's you're basically broadcasting the invalidate on the bus. And this may happen a lot, right? Basically, the first time a processor fetches a block, it gets into a shared state, and if it wants to write to that block, and if it's the only copy, it sends an unnecessary invalidate. If all blocks are like that, you fetch once, write to it, and then some other processor fetches once and writes to it, then you have all the invalidates that are unnecessary, right? And that's the problem. Let's see. Okay, there you go. With the MSI protocol. So the solution is simple, actually. The solution is to ensure that if the processor has the only copy in the block, make sure that that processor knows it with an exclusive bit. Remember the exclusive bit from the directory? This is the same exclusive bit. Basically, if a processor has the only block, if a cache has the only block, make sure that cache knows it by adding another bit into the coherence protocol. Add another state indicating that this is the only cached copy and it's clean. Basically, this is the exclusive state. It's also called the exclusive clean state. Also called exclusive clean. Right? Now the processor can write to that block without notifying anyone. Basically, how do you actually place a block into this exclusive state? When a processor requires a block, let's say the processor doesn't have the block, no processor has the block. This processor does a processor read to block A. That sends a bus read to A, which goes to memory. Memory supplies A. At the same time, what happens is all other processors check if they have A in their caches. If no one has A, then this processor can get the cache block in exclusive state, right? Because that's the only copy in the system. How do you figure out if no other processor has the block? Basically, once this bus read is broadcast, you can have a wired OR signal that ORs the hits of the snoops, right? If this wired OR amounts to 0, this processor and the memory knows that the block actually can be in exclusive state. This processor can set the state to exclusive. That's the idea. You can, through this global synchronization or global bus, you can figure out whether no other processor has the block using a wired OR signal when you request the block. Okay? Basically, snooping caches assert the signal if they also have a copy. If they have a copy, then this block doesn't go into exclusive state, but it goes to shared state. Right? I guess it actually depends on whether the other one's modified or not. This depends on the protocol, but it does go into shared state in MESI. Which means that now if you have an exclusive copy, you can simply write to it and make it modified, right? Silently. Okay? MESI is also called the Illinois protocol because it was developed at the University of Illinois exactly for this reason, to save this bandwidth that goes onto the bus and make it easier for the processor to quickly update the data. This is the classic paper by Papamarkos and Patel. And this is actually a required reading, and I would encourage you to read it. This is the paper. It's only 7 pages. It's a beautifully written paper. There's evaluation toward the end of it. Evaluation is less interesting, but the first 3 pages describe the issues with existing protocols at that point, and actually it describes beautifully how MESI solves the problem. So I would strongly recommend you to read it, and it's a required reading actually. So this is the Illinois protocol, basically. Let's take a look at it. Let's first talk about some definitions. I'll show you the state diagram of the Illinois protocol. Basically, this is what I described to you earlier. There are 4 states, modified. Well, actually, let's look at the processor actions. You can have processor read, processor write. You can have bus read and bus write. And we're going to divide bus write into 2 things. Bus write can be invalidate or bus invalidate, which means invalidate, but the processor already has the copy of the data, so don't supply it. Bus read invalidate means invalidate, but also need the data, which means that the processor starts from a state where it doesn't have the data. So it sends a bus read invalidate. You not only read the data, but you also invalidate, which means that you're writing to it, but you don't have the copy. Right? These are the signals that are asserted on the bus. Bus write, bus read, bus invalidate, bus read invalidate. And there are 4 states. Modified means the processor, the cache has the exclusive copy. I keep talking about processor and cache interchangeably, but because it's a private cache, it's also the processor, right? Okay? So when I say processor and cache, they're the same in this case, because we're really talking about the private cache of the processor. There are 4 states. Modified means the cache has the exclusive copy and the copy is modified, which means that no one else in the system has this copy. The processor has the only up-to-date copy. Exclusive state is the processor has the exclusive copy, but it's clean. Shared state means this is shared. There are at least 2 processors that have this copy, or actually at least 1 processor because something may be invalidated, right? It's shared but clean. Again, we don't know if it's true. At least 1 processor has this copy. Invalid means invalid, right? And this is the state machine. If you look at this, I'd like you to study the state machine. I'll show you different versions of it. But basically, I'll point out one thing over here. Let's say the processor doesn't have the block. It wants to do a processor read. Basically, it sends a bus read signal onto the bus. And if it's only this processor that has the block or that requests this block and no other processor has the block, the block moves to the exclusive clean state. Right? This is what I discussed earlier. It moves to the E state, exclusive state. Whereas if the processor, when it requests the block, and once the processor gets the data in exclusive state, now it can do a processor write and transition to exclusive modified or modified state without notifying others. This is without sending any signal on the bus. Of course, it can do a processor read also, right, and stay in that state. Right. Let's take a look at the other case over here. If the processor doesn't have the block and does a processor read, this sends out a bus read on the bus, and some other processor says, oh, I have the block. Well, in that case, the processor needs to move the state to the shared clean state. Right? Okay? Now, if that other processor had the block, for example, let's say if that other processor had the block in modified state, right? Then it receives this bus read signal coming from this processor going from invalid state to shared state. It receives this bus read signal and supplies this data. That's how the data gets communicated. So what's happening is here, let's say processor 1 is doing a processor read, processor 2 to A. Processor 2 has this block as a modified state in its own processor, and this is block A. And this processor read A. This processor read gets translated to bus read, and this bus read A gets snooped by all of the caches, and this cache says, oh, I have the block. And in this case, it basically supplies the data, goes to the shared state, as you see in this transition, right? It was in the modified state, it receives a bus read, it supplies the data, goes to the shared state. Whereas this processor was invalid, it does a processor read, it sends a bus read, It sees that others have it. This wired OR signal is asserted. Basically, someone has it. So it gets the data supplied on the bus. It goes into the shared state, and it still has A. Right. So no one now has the data modified. That's how you move from a modified state to shared state on this processor, and invalid state to shared state on this processor. Right. Now we'll see an issue with this. Basically, you're still in the shared state, but this one moved from modified to shared. Now you need to update memory also, right, in MESI. Because shared state, the semantics of the shared state is such that there is at least one cache that has the copy and memory has the correct copy, right? Does that make sense? Shared state means memory has the correct copy. Why? Because you don't have a separate modified state. Shared means in this case, oh, there's shared. But we don't have the modified. Someone must write it back, right? This one had the modified copy. It knew that it was modified. So when it's moving from modified to shared state, it needs to write the data back to memory. So at that point, location A is up to date in memory, right? Now that's a problem because even if you're going from shared to state, the data still needs to be written to memory, even though memory may not really need it, right? So we're going to try to fix that problem later. But now this is MESI, right? You can go through all of these different states. Let's take one other example, for example. Okay, well, let's see what should we take. Well, let's do this, I guess. Let's say the processor is an exclusive state. Or actually, let's do this. We write to processor write, right? Let's say the block is an invalid state in the cache. The processor wants to do a write to it. In this case, the processor sends a bus read invalidate signal. Why? Because the processor doesn't have the data. It needs to get the data, that's bus read. And it also should invalidate all of the caches because it's going to write to that block. Right? Now what happens, all of the other caches that have the block, let's say a cache has an exclusive clean state, which means that no other cache has an exclusive modified state. Exclusive means only one cache has the copy. Right? So if a block is an exclusive clean state in one cache, it cannot be an exclusive modified state in another cache. It cannot be in any other cache, actually, in any state. Except for invalid state, of course, right? Let's say a cache has an exclusive clean state and it receives a BRI signal, bus read invalidate signal. It basically goes to invalid state and supplies the data to the processor that's requesting it. Now, if multiple caches are in shared clean state, and if they receive a bus read or bus read in, oh, I guess I don't have the bus read invalidate here. Basically, if they receive a bus read invalidate, one of them supplies the data and also invalidates, and they all invalidate the state. Okay, that needs to be over here. Okay? Okay. So that's the MESI state machine. And this is another MESI state machine, and you can study all of these different MESI state machines. And this is actually the MESI state machine from the 447 lab. If you've taken 447 with me, you've done this lab where you've actually constructed the coherence protocol, MESI protocol, and implemented a cycle accurate simulator that's written in C. And you will remember that. But you can study the handout from 447 as well. But I'll point you a couple of things in this over here. Basically, modified state means that you have a single owner, read-write access, and you have dirty data. Shared state means that you can potentially have multiple owners. They have read-only access, they cannot write, and the data is clean with respect to the memory. So this is the semantics of the shared state, right, that I showed you earlier. Exclusive state means this is a single owner, it has read-write access, and it's clean, right? It can write to it, but when it writes to it, it needs to go to the modified state. So the transitions, some transitions are called downgrades, some transitions are called upgrades. A transition from a single owner state, exclusive or modified, to shared state is called a downgrade because the transition takes away the owner's right to modify the data. Basically, this is how you go downgrade it. You basically had exclusive rights, and that exclusive right is taken away from you. A transition from the shared state to a single owner state, exclusive or modified, is called an upgrade because the transition grants the owner to the ability to write to the block. Right? So you have upgrades and downgrades. And this is another view of Lab 7 from 447. And I'd strongly encourage you to read that Lab 7 if you would like to understand coherence more. And if you haven't taken 447, and if you haven't done that lab, I would strongly encourage you to do that lab. We'd be happy to provide you the code that you will need to do. But it's a fun experience, and it's a lot of it's good work, but it's enjoyable. In the end, you will implement a real protocol, the MESI protocol. And just to prove that it's a real protocol, this is actually Intel Pentium Pro's cache coherence protocol. The slide is credited to Yale Pat. And many of today's systems actually implement some sort of MESI, or Moesi as we will see it. But Intel Pentium Pro implemented the MESI protocol. And you can see exactly the same states over here, right? You have an invalid state, and you have shared clean, exclusive clean, and modified state. And you can see over here, if you can go from invalid state to shared state if actually other processors have the data. Someone has it clean, or someone has it dirty. And you can go from invalid state to exclusive clean state if no other processor actually has the data clean or dirty, right? This is the MESI protocol in Pentium Pro. Okay, there are a bunch of trade-offs in Snoopy invalidation, and let's cover some of them. First of all, when you get a downgrade, should that downgrade go from modified to shared or modified to invalid, right? And you have a choice here. You can go to shared if data is likely to be reused, right, before it's written to by another processor. This processor has the data as modified. Should it go to shared? Should it go to invalid? It makes sense to go to shared if it's going to read the data, for example, afterwards, right? But if it makes no sense to go to shared if it's not going to read the data anymore, right? If data is likely not to be reused before it's written by another processor, you can directly go from modified to invalid. So you have protocol design choices in MESI, also in invalidation. And by knowing more about what will happen to the data, or by predicting that, you can make better design choices. Now, why does it make sense to go from modified to invalid? Well, now you're actually clearing your cache space, right? If you go to invalid, now some other cache block can use that location. Whereas if you go to shared, then this is in the LRU position, least risk in the use position, for example. It takes a while for this block to get out from the cache. Right? So do you do cache-to-cache transfers? On a bus read, should data come from another cache or should data come from memory? Well, again, you have a choice. If going to the memory is expensive, maybe the data should come from the cache, right? If it comes from another cache, it may be faster. If memory is slow or if it's highly contended, right? But whereas supplying the data from memory is simpler because there is no need to wait if the cache has the data first. But this may not be a big deal because you're snooping anyway. But the other advantage is there's less contention in other caches, right? If you want to access the data, then which means that the data array of another cache needs to be accessed to supply the data from cache to cache. If there's lots of contention in that particular cache, you may want to go to memory, although memory is usually slower. If you actually get the data from memory, then this requires a write back on a modified downgrade. If you're actually going from modified to shared, and if you would like to be able to get the data on a bus read from memory, the memory needs to have the correct copy, right? That requires a write back. Okay? Otherwise, you cannot get the data from memory, right? Memory has to have the correct copy on an M downgrade. Okay, one other design choice is a write back on modified to shared necessary, as we've discussed over here, right? One possibility, actually, as I told you over here, you go from modified to shared. In MESI, shared state means memory has the correct copy. It's the clean state, and there can be multiple copies that are clean. Memory has the correct copy, and at least one cache can have the copy in shared state. Now, if you want to go from modified to shared, this means that you need to write back the block into memory. Now, this may not be desirable because if the block is not going to be read from memory, this wastes memory bandwidth, and this takes time, right? So why not get rid of this writing back to the block from modified to shared? When you're moving from modified to shared state, let's get rid of writing the block. Let's get rid of the write back of the block from cache to memory. Now, how do you get rid of that? Well, you shouldn't lose the information that the block is modified. You can supply the data to some other processor, but now the block is modified. And both caches have the block modified. That's different from the memory. So you need to add some other state. Somebody needs to write the data back when the data gets evicted eventually. And that's the idea of an owner state, right? So the Moisey protocol is one other protocol that adds one more state. And one cache basically is designated as the owner. For example, when this cache, instead of going from modified state to shared state, it goes to owner state and somebody else has the data as shared. Owner state means that this is the cache that's responsible for writing the data back to memory eventually. Okay? Basically, one cache owns the latest data, even though many other caches can have the latest data, and memory doesn't have the data. That's what owner state means. And memory write back happens when all caches evict their copies, and the owner is responsible for writing the data back. So let's go back to the problem with Moisey, as I've actually discussed this just now. Shared state requires the data to be clean, right? Because memory has the correct, most up-to-date copy. All caches have the block that have the block have the up-to-date copy, and so does the memory. The problem is, if you're going from modified to shared state, which means that when you have a bus read that happens when the block is in modified state, that cache needs to write the block back to memory. Why is the problem? Well, memory can be updated necessarily, as I showed you earlier, right? Some other processor may want to write to the block again while it's being cached, right? As a result, you'd better keep the data inside here, right? You don't need to necessarily update the memory at that point. So you can improve on Moisey. There are several ideas here. I'm not going to go over all of them. But basically, the first idea could be, do not transition from modified to shared on a bus read. Invalidate the copy and supply the modified block to the requesting processor directly without updating memory. So that's one potential state transition, right? This block was modified in this cache, and this processor requested that block using a bus read. Now, this cache invalidates the block and supplies the block directly to this cache. Now this becomes modified, right? So you don't change the semantics of the states in this case, but modified, and this cache has the only modified copy. Now there could be downsides to this. If this cache is actually going to read the data, well, maybe you don't want that, right? Okay? The second idea is transition from modified to shared, but designate one cache as the owner, as the O state, who will write the block back when it's evicted, right? This is the same idea that I discussed just now. Now, shared means shared and potentially dirty, right? Shared doesn't mean memory has the correct copy. Shared means shared and potentially dirty. Okay? And this is a version of the Moisey protocol that's employed in some systems. And I'd encourage you to read about this more. Okay. So what we've done is basically this, right? We had this valid-invalid protocol. We moved to MSI, and we've seen there are some limitations to MSI. We moved to Moisey, and then we moved to Moisey, right? And the limitation of MSI was when you read the block the first time, it went in the shared state, so you couldn't exclusively update it, right? You needed an additional invalidation, even though this was the only block, only cached copy in the system. You need that additional invalidation to be able to update the block, going to the modified state. So we eliminated that. And then we added more states. We went to Moisey. So this added some complexity into the system, right? This required determination of whether or not this is the only shared block, only copy of the block in the caches. And also an additional state. Now you have 2 bits. Well, you had 2 bits over here, but the protocol becomes more complex. Now we realized the problem with Moisey, which is this transition from modified to shared state that required update of main memory. So we got rid of it by adding another state, owner state. Now we have 3 bits per cache block. So this made it more complex, right? But we actually got rid of some more inefficiency in the coherence protocol. So you can keep optimizing this coherence protocol with more state and potentially prediction mechanisms, right? You can predict whether you're going to use the data and transition to from modified state to invalid state, for example, if you're not going to use the data. You can add all of these sophisticated mechanisms, and these are good because they reduce unnecessary invalidates and unnecessary transfers of blocks between cache levels, between caches, as well as between caches and memory. This is the upside. However, as you add more states and optimizations, it becomes more difficult to design and verify the protocol as well as the predictors. Why? Because this leads to more cases to take care of, more race conditions. And coherence protocols are actually difficult to get right. In this case, Snoopy coherence protocols are easier to get right. Directory-based cache coherence protocols can be harder to get right, actually, as we will see. But basically, you have more. It becomes more difficult as you add more states, right? And the other downside is they provide diminishing returns. The benefit you get from going from MSI to MESI is much higher than the benefit you get from going from MESI to Moesi and Moesi to Moxesi, for example, right? Basically, you get diminishing returns. You get that diminishing return curve. Of course, depends on the workloads, but on average. So it's important to think about where you draw the line in optimizing your coherence protocol. This is a very interesting area, and there has been many works that were done for decades on optimizing the coherence protocol. And I'd be happy to give you some pointers if you'd like to do a project on this. So let's revisit these two cache coherence methods. We've talked about Snoopy bus and directory. Let's take a look at what are their advantages and disadvantages compared to each other. Snoopy cache or Snoopy bus, the upside is big. The big upside of this is miss latency, or the critical path is short. Basically, when you get a cache miss, there is no indirection, right? Because there's a single point of serialization over here for everything. You basically have a bus transaction to memory. Everybody sees that transaction, right? And that's the key upside. A miss doesn't require an indirection to the directory. It's short. The critical path is short. Global serialization is easy. Bus already provides this, right? So you have this arbitration, which is nice. It's simple. You can adapt the bus-based processors easily to this, right? You don't need to add a directory, for example. You can easily adapt the bus-based processors. The downside is it relies on broadcast messages to be seen by all caches in the same order, right? Which means that you either need a single point of serialization or bus, which is not scalable, right? Basically, this broadcast needs to be done in the same order. All processors need to see all of the broadcast messages in the same order, right? Bus makes it easy, but bus is not scalable, which means that the scalability of these Snoopy protocols is limited. You can have a virtual bus. Basically, you can have a totally ordered interconnect that acts like a bus, but the underlying interconnect is not a bus. But that's actually very difficult to design. Very difficult to design a totally ordered interconnect that's not a bus. And I'd encourage you to think about it. How do you, for example, make a torus look like a bus? You can actually have an ordering of traversal of the torus, but then that limits your choices of how you would go about routing in the torus, right? So it's interesting to think about it, but it's very difficult to design a virtual bus on another physical substrate than bus. On the other hand, directory, the downside is exactly the opposite of Snoopy cache. Basically, it adds indirection to miss latency, critical path. Now, a request doesn't just get the data quickly, but a request needs to go to the directory and perhaps generate some acknowledgements, and after that, go to the memory. There's an additional hop. Directory requires extra storage space to track share sets. This doesn't happen in the Snoopy protocol. Snoopy protocols, you get extra tag bits for every cache block. Whereas with the directory, for every block in the system, you need to track the share set. Right? Whereas with the Snoopy protocol, you just need to keep track of the state of the blocks that are just cached. Right? You don't need to keep track of the state of blocks that are in memory but not cached. Okay? So the upside of the directory is it can be approximate. False positives are okay, because if you do not know whether or not a cache has the block, the directory is approximate. It can use Bloom filters, for example. Then basically it sends invalidation requests to those processors that to the superset of processors that it thinks might have the data. In that case, if the processor doesn't have the data, and if it gets an invalidation request, it just drops the invalidation request, right? Okay? So in directory, the protocols and race conditions can be much more complex, especially if you want high performance, because the directory can now do the optimizations that I described to you earlier, right? The directory can say, oh, processor 1, you're actually close to processor 3 over here, which is requesting the data. So why don't you send that data directly to it? Now it requires a lot of acknowledgements to ensure that this really happened, right? Because directory is orchestrating the action, but the action is happening on an interconnect that's totally unordered, and the processor needs to notify that both processors need to notify the directory that they have received the data and they've done the correct thing. Okay? So this kind of optimization is enabled by the directory, which is nice, but also this protocol can make it more complex to verify and design. The big upside of the directory, which is already up here, it decided to come up quickly, I guess, it doesn't require broadcast to all caches, right? The directory can selectively choose which caches it should invalidate or which should update, right? Whereas with a bus, there is a broadcast that's needed. With a Snoopy protocol, there's a broadcast that's needed. And because of this, actually, because the directory can keep track of the share set in a scalable way, and it can basically directly deal with the shares, it's exactly as scalable as interconnect and directory storage. It doesn't require this virtual bus, so it's much more scalable than bus. In fact, directory protocols have been implemented on all kinds of interconnects, including Torus, including meshes that are very different from buses. Basically, this looks like a mesh, right? Okay. And this is, actually, this is a 4x4 mesh, and you have nodes here, let's say, and you have caches associated with each node, each processor. And these caches can be employing a directory-based cache coherence protocol, right? And the directory can be distributed to different memories, right? You have different memory channels, memory 0, memory 1, and directory 1, directory 0, right? And maybe you have other memory channels over here. Memory 2, directory 2, and memory 3, directory 3, right? Okay? Now, how do you make this more scalable? Now, the one problem with directory is basically if this processor is trying to access some data that resides in this memory, it first needs to send a request to the directory saying, oh, I would like to access this data. And this directory needs to send invalidations potentially if it's a read exclusive request, and then send the data, right? Send the cache block. Now that takes a while, all the way going to the directory, right? So how do you scale this? Basically, people use directory caches, right? You can cache the directory in designated nodes. For example, you have a directory cache in each node, right? And the addresses that are cached, basically these contain the share sets or directory entries for a subset of addresses, and that subset of addresses can be statically mapped to these different nodes, right? So that's how you can reduce the latency of access to the directory by caching the directory in individual nodes. Now, in that case, if this processor needs to do a read exclusive access to memory location 0, let's say, let's assume that this memory location 0 is cached in this directory, location in this distributed directory, then this processor needs to send a request to this cache, directory cache. And this directory cache can now control, because it has the full information share set for this particular block. What does it save? Well, this saves an extra trip all the way to memory, outside the chip, right? And you could actually potentially move the directory cache entry somewhere closer over here. And we're not going to go into that, but directory protocols can be optimized to be even more scalable this way. Okay, let's revisit directory-based cache coherence quickly. Again, I've already given you actually a lot of the issues that I wanted to discuss, and we've already covered this, so I'm going to go through this relatively quickly. Basically, directory-based protocols are especially desirable when scaling the system past the capacity of a single bus. Right? It's distributed, but coherence still requires single point of serialization in the directory because you need write serialization for a given block. But serialization location can be different for every block. It can be striped across nodes, and that's what I'm showing over here to you. Basically, serialization location for a block is in memory, somewhere here. This is in the directory, but this could be a separate place. And also, when you cache the directory, serialization location can be striped across the blocks. For example, this directory cache can contain block 0. Block 1 can contain the directory information. This particular node can contain the directory information for block 1. This node can contain the block directory information for block 2. This node can contain the information for block 3, block 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Well, I guess I've added a mesh that's greater. That's okay. Let's assume that this is a mesh that's of 16. And block 16 can be here, 17 can be here. This way you've striped the addresses statically across all the nodes in the system, all the processors, all the caches, all the distributed directories in the system. This way, your serialization location for address 4 is in this node. And you can know that by just looking at the address. If this processor needs to do a read exclusive access to address 4, you can determine by looking at the bits of address 4 that the serialization location, the directory request, needs to be sent to this node. This way, the directory requests are actually distributed, and your load can be balanced across the system when you have coherence requests to different nodes. Okay? That's the beauty of a directory, actually. Now, you can reason about the protocol for a single block, right? For a single block, actually, you have one server and many clients. The serialization location, the directory node, can be stored as a server, right? And there could be many clients, the private caches that need to access that particular block, need to access that directory node, need to access that server, asking for a copy of that block, and asking the server to do stuff for them such that they can do the right thing for that block. You can think of the directory that way, right? And you can reason about the protocol for a single block. You don't need to reason about the protocol for all the blocks. Basically, directory receives read and read exclusive requests and sends invalidation requests. And invalidation is explicit, right? It's an explicit invalidation request that's sent out. As opposed to Snoopy buses. Because the directory, let's say, receives an exclusive request to block 4 over here, and it has, let's say, shares 0 and 16 and 24. Well, 24 doesn't exist here. 0 and 5 and 7. It basically sends invalidation requests to node 0, node 5, and node 7. Right? And this could be sent separately. Right? Invalidation is explicit. So that's one interesting fact about directory-based protocols that makes them more scalable. One other thing is, how do you actually keep track of the share set? This doesn't necessarily need to be a bit vector, right? Because bit vector doesn't scale well as you increase the number of nodes. You need to add a bit per node, right? But the key operation is to support the set inclusion test, right? For basically a shared block over here, you need to ensure that you at least send invalidation requests. You at least know a superset of shares, right? In this case, false positives are okay. You want to know which caches may contain a copy of the block, and you can send an invalidation signal to all caches. Actually, you don't need to. You can broadcast to the all caches, and the caches that do not have the block can basically ignore the invalidation request. I told you this earlier, right? So basically, you can reduce the size of the data structure from you don't need to keep the exact share set, but you can keep the superset as long as you're conservative. You can reduce the size of this directory data structure, but now when you have false positives, you have extra invalidations. That's the trade-off you're making. The size of the directory versus extra invalidations. And false positive rate determines performance, of course. The most accurate representation of the share set and the most expensive is the full bit vector. Actually, it could become more expensive, but let's keep full bit vector right now. Full bit vector requires a bit for every node in the system in the directory node. So you could actually compress this. That's one representation. If you have lots of zeros, for example, compressing may be a good idea. You could have a linked list representation. Basically, the share set can say, oh, node 0 has this block. Let's say for block A, the share set is node 0, and the next one is none. This is nice if only a few nodes actually have the block, right? Because now this could be actually a smaller data structure than a full bit vector for all the nodes in the system. Think about a system that has 64,000 nodes. This means that you have 64,000 bits per every block in memory in the directory. That's expensive. Whereas if you actually have a linked list, you only need to encode the address of the nodes that actually have the block, basically the address is only 16 bits, right? And if on average you have only one block that's sharing a particular block, you can get away with approximately 16 bits per directory entry, right? Instead of 64K bits. So that's the idea. You can actually have a linked list representation. You can have a Bloom filter representation. Basically, in this case, instead of having a bit vector that has 1 bit per node, you basically have a smaller bit vector, right? That's the idea of a Bloom filter. And I'm not going to go into Bloom filters in detail, but I'll encourage you to read some papers that are related to this. Actually, I'll give you one paper that is very good to read, and this will be a recommended reading. The paper that describes the Bloom filters as well as works on it I'll actually give you 2 papers. An application of Bloom filters. It's good to read the application of Bloom filters. One is the evicted address filter. Basically, this is published in PACT 2012 by one of my students, Vivek Seshadri, and co-authors. And the idea is to use a Bloom filter to keep track of the blocks that are evicted from the cache in an approximate way. And check this Bloom filter when you get a cache miss. And if the cache miss actually hits in this Bloom filter, that means that you've evicted the block prematurely, because you've actually accessed this block right after you evicted it from the cache. And this way you can design an insertion policy into the cache saying that, oh, if this block that I've accessed is actually in this evicted address filter, Bloom filter, then I'm going to insert this block with high priority into the cache because I've done the wrong choice for this block, because this block actually has high reuse. Okay, the second paper that I'll recommend is the paper Raider that also uses Bloom filters for a very different purpose: retention aware intelligent DRAM refresh. Okay, I'm not going to write the entire thing, but I'll very strongly recommend you to read this paper. This paper is published in ISCA 2012 by my group. And again, the idea is to keep track of the set of blocks that do not need to be refreshed very often in DRAM. And you can keep track of the set of blocks or rows that do not need to be refreshed very often using a Bloom filter, because this enables you to actually reduce the size of this data structure that needs to be kept. And that's the same idea. That's a very similar idea in the directory over here. You can reduce the size of this huge bit vector by using a Bloom filter. That's an approximate data structure. Basically, Bloom filter is an approximate data structure to represent and test set membership. And test set membership. And I'd strongly recommend that you read about Bloom filters. And the seminal paper that was described by Bloom in CACM 1970. Again, I'll strongly recommend that paper to you, as well as these other papers, so that you can apply Bloom filters. Because Bloom filters can be a very useful tool in whatever you design in the future, both in software and hardware, because this data structure is generic. It could be software data structure, it could be a hardware data structure. Whenever you would like to represent some set membership in an efficient way, you can use Bloom filters to do that, as long as approximate way is okay. In this case, approximate way is okay because you can send additional extra invalidation requests to blocks that do not have it, as long as you can represent a superset of the set membership. Okay, some basic operations. Basically, directory-based protocols and Snoop-based protocols are at some point very similar because they follow the same semantics. You can actually implement the same high-level protocols, MSI, MESI, Moesi, either on the directory or Snoop-based protocols. That's also orthogonal, right? So directory-based protocols follow the semantics of the Snoop-based system, but with explicit request and reply messages. Directory receives these read exclusive, and upgrade requests from nodes, and sends invalidation and downgrade messages to sharers if needed. It forwards the request to memory if needed. It replies to the requester and updates the sharing state. So protocol design is very flexible because of this, right? Exact forwarding paths, exact things, exact messages actually depend on the implementation. For example, do you actually do a cache-to-cache transfer? Let's take a look at an example over here. Let's say we have two processors. Well, actually, in this case, we have one processor. Processor 1 does a read, and the home node is actually the node that, this is actually another terminology that you should be familiar with. Home node is the node that actually has the directory entry for a particular address. Home node of A is the node that has the directory entry for address A. In this case, for example, address 4. Home node of 4 was this node, right? Well, it happens to be 4 over here. Okay. So P0 acquires an address for reading, and the data is sent through the home node in an exclusive fashion, right? Or in a shared way, depending on the state of the block in the home node. Or, if you want to do a cache-to-cache transfer, the home node can say, oh, processor 1 actually has the data, and processor 1 is much closer to you, so I'm going to notify processor 1. Home node sends a request to processor 1, saying, processor 1, processor 0 is requesting this block that I know you have, so send it to processor 0. Right? So that's what happens. Of course, doing something like this requires acknowledgements, right? Or it requires a directory to know that processor 1 actually definitely has this data, right? So what does this mean? Which means that when the processor 1 evicts some data from its cache, it needs to notify the directory then, right? That may not be a good idea. So acknowledgement may be a better idea. Home node sends to processor 1. Processor 1 sends this data to processor 0 and acknowledge that you sent it. So there needs to be an acknowledgement coming back. Because how does the home node ensure that processor 0 gets the data, right? It's good to think about. So let's look at another request. Let's say we have processor 0 sending a read exclusive request to the home node over here. The home node figures out that this block already has an owner, and it sends an invalidation request to the owner. And the owner can send a revised copy. Owner means in this case, it has a modified copy, right? The directory doesn't have the up-to-date copy. So owner sends a revised request, revised data back to the home node. And it can also send the data to processor 0 as long as the directory told it that processor 0 requested it. So you can optimize the protocol this way, right? And this makes sense, especially when the owner is very close to processor 0, the requester, right? And the directory can have that information, right? It can know the interconnect topology of the system, or it can figure it out. And then it can basically decide to do the cache-to-cache transfers in these different cases, right? Let's take a look at one other interesting thing, which is contention resolution. Let's say both processors, processor 0 and processor 1, want to write to a block. They do a read exclusive request, and this goes to the home node. And home node returns the data to one of the processors, and it needs to do something to the other processor, right? If you have this kind of collision or kind of a race contention for a given block, one processor becomes happy and the other processor should be unhappy. And what happens when the other processor should be unhappy? So this protocol is one example. Basically, it's called a NAC, negative acknowledgement. The home node tells processor 1, sorry, processor 0 requested it, and my fairness policy says that I'm giving it to processor 0. So try it again. NAC means try it again, processor 1, right? And processor 1 becomes unhappy, and after a while, processor 1 tries it again, and the home node sends an invalidation request to processor 0, and processor 0 sends the revised copy back to the home node and also sends the exclusive copy to processor 1. Well, why do you have this path? The home node can actually be the middleman. You could actually do that, but it may make more sense to, especially on an unordered interconnect that has a lot of bandwidth, it may make more sense to have the data from processor 0 transferred to processor 1 directly, right? Because it may so happen that processor 0 is here, processor 1 is here, and the directory is here, right? The directory still wants the data, but, well, it may not want the data either, depending on the protocol, but it definitely wants that cache-to-cache transfer to happen very quickly over here. Make sense? Okay, there are several issues with contention resolution. First, we need to escape race conditions by knacking requests to busy entries. Basically, if two requesters try to get exclusive access, you can knack one of them, right? Now this means that the original requester retries, And you can have lots of NAC traffic if there's a lot of write contention at the same time. Or there's another approach. You can queue the requests, right? The directory home node can buffer the requests and grant them in sequence. This is nice because this doesn't require the retries. There's no NACing here. Of course, the downside is now you have a queue. You have a buffer. And how large should that buffer be, right? And if that buffer overflows, what do you do? So you can actually have a combination thereof, right? You can actually combine NACing with buffer. When the buffer is full, you can NAC the request from now on. Okay? So fairness is an issue. Which requester should be preferred in a conflict, right? Should it be processor 0, processor 1? Is one of them more critical for some reason? This is interesting, right? And in this case, the delivery order matters, the distance matters. Maybe the directory wants to grant the request to the close by node, or in some order such that the data percolates across the network. So there are a lot of interesting issues related to contention resolution. There's also ping-ponging, but this is a higher level issue. When ping-ponging happens, it's usually because you have some invalidation traffic that happens because you actually have a bad synchronization mechanism. You can eliminate ping-ponging at a higher level by designing your locks and barriers or designing your shared structures in a better way. And we're not going to talk about that in this lecture. So scaling the directory. This directory is a scalable structure, but actually what happens if you want to scale it to nodes on the order of 64,000 or 100,000? First of all, I'll leave you with some questions. I'm not going to give you answers, but how large is the directory? That's an interesting question, right? Where should it sit? Should it be distributed? How can we reduce the access latency to the directory? And I've already given you the answers, right? If you have a single monolithic directory sitting in memory, that means that you're going to keep the share set and information per block information for every block in memory. And that could be very large, right? You could think about blocks, cache blocks of sizes of 64 bytes, and main memory that has, let's say, 32 gigabytes or 1 terabyte. 1 terabyte is a large number, by the way. 32 gigabytes is 2 to the 35, but I believe 1 terabyte is 2 to the 40. Assume that you have 2 to the 40 bytes in memory, and your blocks are 2 to the 6 bytes. Then the directory needs to have 2 to the 34 entries, right? That's huge. Okay, think about it. So scaling the structure may not be that easy. Okay, how can we reduce the access latency to the directory? Well, you could distribute the directory, as I've shown. You could cache the directory entries, as I've shown over here, right? How can we scale the system to thousands of nodes? Again, directory protocols need to be optimized. If you require a lot of acknowledgements, and if you send a lot of invalidations, well, that may not scale too well. And the last question is, can we get the best of snooping and directory protocols? Basically, remember the snooping protocol gives you low latency. You don't have this indirection on the missed critical path. But the downside is it requires a virtual bus, which is very hard to build in a scalable way. The directory protocol, the upside is it can be scaled to any interconnect, right? It can actually work with any interconnect nicely. It's scalable. The downside is it has this additional latency, right? Which is going through the directory. So actually, with whenever you have these multiple things with different trade-offs, heterogeneity is the right answer. Basically, can we design a more heterogeneous protocol in some manner? And one option is token coherence. This is one of your readings, and I will briefly discuss that soon. But the idea of token coherence is to decouple the notion of performance and correctness in the design of a coherence protocol. Correctness can be satisfied with some invariant by keeping some invariant. And as long as that invariant is satisfied, you're fine, you're safe. But for performance, now we can potentially design a directory protocol that is not necessarily correct, right? Or that relies on this correctness substrate to provide coherence. Okay, that's all I have. Maybe I'll briefly talk about token coherence in a little bit. Let me first cover reference readings. These are the readings that you should really do. And there's some other recommended readings, and I'll briefly talk about research and then briefly talk about token coherence. Today, as we build larger line, larger scale many-core systems and heterogeneous systems with accelerators, it's important to keep coherence so that programmer actually has a nice view of the system. But it's interesting to figure out mechanisms. It becomes even more interesting to figure out mechanisms to scale coherence to thousands of nodes. And there are some papers that discuss this. And there's also another avenue, which is, do we actually need coherence in some cases? If you can eliminate the burden of coherence, in some cases, that becomes a very interesting proposition today, so that you can scale the systems. So these papers talk about those issues. Waypoint, scaling coherence to 1,000 core architectures. Cohesion, a hybrid memory model for accelerators. This looks at software and hardware-based coherence and tries to combine them in an intelligent manner. And there are other ways of potentially eliminating coherence. When you have heterogeneous architectures, for example, CPUs, GPUs, some accelerators, what kind of coherence guarantees do you need? It'd be good to have everything coherent, but it may be very difficult to scale the system because coherence has its own overheads, as we've discussed, right? And finally, token coherence is a recently proposed coherence method that decouples performance and correctness. Some related videos, basically these are the multiprocessor correctness and cache coherence videos, spring 2013. I would also recommend the cache videos in spring 2013 if you would like to brush up your knowledge on caches. This is called the caches and advanced caches. And there are some related fun exam questions that you can have from 447 exam in spring 2013. But let's take a look at token coherence very quickly because I think this is an interesting approach, and going forward it would be interesting to look at scalable coherence protocols that exploit heterogeneity like this. Basically, these are slides from Milo Martin's PhD thesis defense, and I'd encourage you to take a look at that if you're interested in this. Basically, there are three desirable attributes in a coherence protocol. You want low latency, cache-to-cache misses, because that's fast. You don't want bus-like interconnect because it's not scalable, and you want to be bandwidth efficient. And this is dictated by workload and technology trends. And let's take a look at the workload trends. Commercial workloads actually have many cache-to-cache misses, and these consist of clusters of small multiprocessors. And there are two goals. First, you want direct cache-to-cache misses. You don't want a directory-based protocol because it has this additional indirection to the directory. And you want scalability, of course. And this is the bus-based protocol, if you wish. The processor basically broadcasts its request, and it gets it from some other processor. We want that. But we don't want a directory protocol that has this additional hop. That's a second hop. Right? Workload trends basically favor snooping protocols. Right? Because you want these direct cache-to-cache misses very quickly. You don't want this additional latency, because these are also latency-sensitive workloads. Okay. So snooping protocols are good because they give you a direct request and direct response very quickly, low latency. But the problem is they do not satisfy these two other requirements that we wanted. They require virtual bus, which is difficult to implement on unordered interconnect. Well, you want a totally ordered interconnect, basically. But they're also not bandwidth efficient because you need to broadcast always, right? That's not what you want to do. On the other hand, technology trends actually favor scalable interconnects, right? You want high-speed point-to-point links because buses are not scalable as you keep scaling the system, as we've discussed, right? You don't want a bus. And you don't want a processor memory interconnect that looks like this either, because basically this is a processor memory interconnect that has intermediate routers over here. These are processors and these are memories. You can think of them that way, or nodes and nodes. This is not very scalable anymore because you have these states that do almost nothing. You want glueless multiprocessors that can scale nicely. You basically have, remember the Piranha design that we talked about in multi-core systems lecture? Basically, you want to be able to plug a node, and that node nicely scales. Is nicely added to the system. This improves cost and latency characteristics. And we want something like this, basically. You want some low latency interconnect, and you want a scalable interconnect, and you want to avoid the virtual bus ordering on this interconnect, right? You can actually have virtual bus ordering, which means that you have a very scalable interconnect with lots of bandwidth, but you always go through the same order to satisfy requests. And even then, it may be difficult to get to work it correctly. Get it to work correctly. Okay? So technology trends actually favor unordered interconnects, right? Which means that technology trends are good for this. Basically, yes, no ordering is required from a technology point of view. Yes, you can avoid broadcast, but unordered interconnect doesn't have low latency. So how can we get the best of both worlds? Basically, the goal is all three attributes at the same time. And step one that token coherence provides is you can get low latency without a bus-like interconnect. And hopefully at some point, somebody can improve it to become more bandwidth efficient. So token coherence, I'll give you the key insight. I'll refer you to the paper. Basically, when you have invalidation-based coherence, there's one single invariant. You can have many readers at the same time, or a single writer, right? Remember, when we designed the MSI protocol, or MSI protocol, you only have a single writer at any given point in time. And this is enforced by globally coordinated actions, right? In a bus-based protocol, basically, you have a globally coordinated action to enable this invalidation, right? In a directory-based protocol, also you have a globally coordinated action that's coordinated through the directory. The key idea in token coherence is basically take this invariant, and this is a safety invariant, and satisfy it in some other way that's not dependent on the interconnect. Basically, enforce this invariant directly using tokens. You have a fixed number of tokens associated with each block in the system, and a processor, when it needs to read the block, it just needs to get one token. But a processor that needs to write to the block, it needs to have all of the tokens to write to the block. Right? As long as you circulate these tokens and do not leave these tokens in the system, and ensure that these invariants are satisfied, you can design an invalidation-based cache coherence protocol that's independent of the interconnect. So that's the key insight. You can enforce this invariant that's needed for invalidation-based coherence by using directly only tokens. And as long as you satisfy that, you're safe. As long as you satisfy this invariant, you're safe. You need this invariant to be satisfied, and you also need forward progress guarantees, of course. Right? So this guarantees safety in all cases. This global invariant enforced with only local rules. Local rules meaning a processor checks whether it has all the tokens. Of course, it should be able to request all the tokens, right? There needs to be some protocol through which it can request all the tokens. Right? And this is true. This guarantees safety independent of races and request ordering and interconnect, etc. As long as you satisfy this invariant. So you need to design a protocol that satisfies this invariant. And there are several steps to token coherence, which I will recommend you the paper to read about. Basically, you can have token counting rules to enforce safety. And the safety is basically, if a processor needs to read a block, it has to have one token for that block. If a processor needs to write that block, it has to collect all the tokens for that block. And there needs to be persistent requests to prevent starvation. How do you get all the tokens for a block, for example, or how do you get any token for a block? Now this enables the ability to decouple correctness and performance in cache coherence protocols, right? You can have a correctness substrate that basically maintains those invariants and enables this persistent request to prevent starvation. And you can have a totally different transfer policy that's optimized for performance. So you have two protocols now. And the paper explores 3 different performance policies, which I would encourage you to read. And that's all I have for the cache coherence lecture. Thanks for your attention. And this is a very exciting topic also. And it's becoming interesting again as systems become much more scalable and as systems require different kinds of coherence protocols, perhaps hybrid protocols, heterogeneous protocols, and perhaps protocols that have some coherence and that do not have some coherence. So more hardware-software interaction is needed to scale coherence to large-scale systems that we have on chip today. Basically getting rid of a lot of the overheads that we have in coherence protocols. For example, home node access overhead would be an interesting research topic going forward as well. But I'd be happy to talk